So let's review some of these learning goals that I just went through in that previous video. So know Hooke's law, harmonic motion, and how these build up the potential energy operator for vibrational motion, 1/2 kF x squared. So be familiar with solving the harmonic motion or sometimes harmonic oscillator. Sometimes it's even called the simple harmonic oscillator model. Okay, so just be familiar because I kind of showed you how we can't quite even solve it really. I mean, we can, but beyond kind of the scope of the class. And so these Hermite polynomials, right, those gave us the solution. So be familiar with the Hermite polynomials and their properties, such as the recursion relation. So that chart that I showed you that shows their integrals. Okay, so know the solution to the harmonic motion Schrodinger equation for energy and displacement scale. So that's kind of being able to recognize those equations, you know, E equals nu plus 1/2 times h bar omega. Also, we recognize that the oscillator frequency, right, is the square root of kF divided by m. And I also talked about this displacement scale, this term alpha, how that really sets our displacement scale. Okay, and so now what's coming next is how to normalize the Schrodinger equation for this simple harmonic oscillator model. So let's do that, okay? And so we're going to take advantage of this property of the Hermite polynomials, okay? So let's see, and I'm going to write this just as it was written in the book, where I'm writing like psi nu of x equals n sub nu times h nu of y e to the negative y squared divided by 2, and write x equals alpha times y, okay? And we know the alpha is that big collection of constants, okay? So now we have this thing put together already, right? And so we know to normalize this function, it's going to be given as 1 equals, right, this normalization constant squared. And in this case, by our boundary conditions, we integrate from negative infinity to positive infinity, right? The large displacement. You can see I've got that picture right there. Okay. And that's going to be, right, psi star psi dx, right, to do the normalization constant. Okay. And so now if we keep going here, okay, because we know that if we have x equals alpha times y, then dx has to equal alpha times dy. So we have to keep track of that coordinate transformation, or really just using a different letter. All right, so now if I plug all of that in and knowing the form of our psi, right, of our wave function, okay, we know alpha is a constant, so that's going to come out in front. So I'm going to replace this dx with alpha dy, okay? So now that's alpha. We know the normalization constant stays in front of the integrand, okay? And so now let's see, I still integrate from negative infinity to positive infinity, okay? And then now I know that the rest of my wave function is going to be the Hermite polynomial times this e to the negative y squared divided by 2 function, all right? Well, when I do that, right, I'm squaring it, psi star times psi, and there's no imaginary numbers in there, then what I get is something that looks like this. H nu of y times H nu of y. And then, of course, we square the e to the negative y squared divided by 2, which just becomes e to the negative y squared dy. And then now check it out. This is pretty cool. We actually have a guide for how to solve this. Look at this. H nu prime times H nu times e to the negative y squared dy equals 0 if y prime cannot equal, or excuse me, if nu prime and nu are different states, it equals 0. Orthogonal wave functions, that makes sense. But look, if nu prime and nu are the same, as in the case of trying to normalize this, then we get a fairly straightforward solution for this thing. Okay, and so now that means all of this is 1 equals, and I still have this alpha times normalization constant squared out in front, But now this whole integral is just going to become the square root of pi time. Sorry, I'm going to make myself a little bit more space. So we know that it's 1 equals alpha times that normalization constant times pi to the 1/2, so I'll just write that as square root of pi, times 2 raised to the new power times nu factorial. Don't forget about factorials, okay? And so now I just have to algebraically rearrange this for the normalization constant. And when we do that, we get the following: 1 over alpha, I guess I will write pi to the 1/2 because I've got that square root right there. I'm going to have a square root of a square root. Times 2 nu times nu factorial all square root. Okay? So this becomes our normalization constant. And what's important to note, it contains that alpha term, okay, which gives us our displacement scale. So I want to talk more on this displacement scale. And now that we have got a normalization constant, we can also see what the wave function actually looks like, okay? So here this graph is showing you what psi looks like in the red and what psi squared looks like in the blue. They both look very similar. They have the function of a Gaussian distribution because that's that e to the negative y squared divided by 2 term. That's what that's giving us, all right? And also, if you notice, when this displacement scale is unitless, so when it's set up as x divided by alpha, we get these really easy whole number integers we can see on the scale, like 2, 4, etc., okay? And also, I'll just remind you, right, this model describes particles on a spring oscillating back and forth, and you can see from psi squared what we get, the most likely place to find the particle, you know, is somewhere in the middle. And as this displaces, as it stretches out, we find less and less probability of finding it there. So now what happens, so this is for the case of nu equals 0, which we're going to call the ground state. So now this is the case for nu equals 1. And so you can see psi is in blue and psi squared is in red. And you can see they both predict the same thing, all right? So very similar to the particle in a box model, we're now getting these integer waves, all right? And then now what you can also see is we have a node in the middle, okay? And so now if you look over to my Mathematica file here, oops, let me go to this one here. I've got them labeled, all right? And so these are actual calculations. This is a pretty fun, cool little figure I made. So you can see here is that nu equals 0, that ground state, where the particle is predicted to be kind of right in the middle. And notice what happens as I go up to nu equals 1, I predict a node in the middle, and the probability distributions are moving out towards what I'm going to call the turning points. So the turning points are as it stretches out and then recoils, right? And stretches out and recoils. And you notice as we keep going up and up and up, we get smaller probability of finding the particle in the middle. So I know it's kind of hard to see, but these, for nu is 4, right? These 1, 2, 3 peaks in the middle, those are lower probability than the peaks on the outside, all right? Which is pretty cool. And so I want to talk a little bit more about this displacement scale and this whole notion of M, all right? Because what you might be thinking right now, I've been drawing these two masses on a spring, M1 and M2. So what does that mean for M right there? Okay. Well, recall, we have to use the reduced mass when we have a two-body problem like this. So this M we're talking about here is the reduced mass of our two masses, all right? And so I'll remind you, reduced mass gets the Greek letter mu, and that goes as M1 times M2 over M1 plus M2. And of course, if M1 equals M2, then my reduced mass just becomes the mass, right? It becomes the same parameter, okay? Or excuse me, I let's work that out. So if m1 equals m2, we'll just now say it's m times m over m plus m, which is m squared over 2m, yes, which is 1/2 m. Apologies. Yeah. So if m1 equals m2, then we know the mass is just 1/2 m. Okay. And if we go through our dimensional analysis, all right, this m has to be in units of kilograms per single thing. So if we're talking about electrons, that's got to be a kilogram mass of one single electron. If we're talking about atoms, which we will very shortly, it's got to be the kilogram of one molecule. So we're not talking about kilogram per mole. We're talking about kilogram per one single thing. All right. So now, what if our two masses are very different? And I'm going to draw up a cool example. What if my mass 1 is, I'll say, mass of a proton, and what if my mass 2 is mass of an electron? Well, those two masses are very different. They're different by a factor of about 1,000. So mass of the proton is much, much greater than mass of an electron. And so what if I was describing this, right? I have this picture where I've got a proton and an electron, and perhaps the electron is oscillating back and forth with the proton, okay? Maybe as it's orbiting around our nucleus, right? We're going to start trying to build this physical picture. Well, what is the reduced mass of this pair? All right. Well, as it turns out, the mass of the electron times the mass of the proton divided by the mass of the electron plus the mass of the proton is basically just equal to the mass of the electron. That's right, okay? And the reason for that is because the mass of the electron plus the mass of the proton, right? The mass of the electron adds hardly anything to it. It barely changes the number, okay? And so because the mass of an electron plus the mass of a proton is basically just equal to the mass of the proton, then mass of the proton and mass of the proton cancel, and you just have an object that's only the mass of an electron. So what does that object look like? Well, it doesn't look like this picture that I drew with two masses on a spring. What it really looks like is some massive object that I'll call mass 1 that's fixed, okay? And now mass 2, in this case would be the mass of the electron, is now oscillating just against this fixed mass, okay? So in this example, right, of this like electron system, one electron system, let's say, it appears as our nucleus, or our proton, if you will, is stationary. It's stuck there in the middle while this electron is oscillating back and forth. So now as you look at this model, what I want you to imagine, nowhere in this picture is the proton, okay? Rather, if I go back now, and if we think about this picture right here, so here's my potential energy, okay? So my electron, what it's really doing is just oscillating back and forth between those two turning points. So, you know, here's my nucleus, some stationary object, right? And so now my electron just looks like it's oscillating back and forth right here, giving me my displacement scale. And also you can see based on the wave functions, it kind of makes sense that in the ground state, we predict it to be somewhere there in the middle, right? Oscillating somewhere in the middle of that displacement, okay? Which is pretty cool. And what I also want to say, what we can expand on this, we don't just have to use this model applied to protons and electrons. We could apply this model to actual molecules, all right? Which is pretty cool. So here, I kind of spoke out of order. So here, you know, I'm showing you the Mathematica file over here, but here's the results of it, of psi squared, right? And here is just psi, okay? And what's important to note, as nu gets bigger, we see more probability being pushed out to the turning points, okay? So more and more and more displacement as nu gets bigger. And what that means, that displacement, we're talking about this displacement scale just now, right? So that depends on the oscillator strength, Kf, also depends on the mass, right? If we're talking about this electron-proton system, or maybe we're talking about hydrogen chloride, a hydrogen and a chlorine vibrating back and forth, okay? And so what we expect, anytime we have two very different masses, one very light mass, one massive mass, this is what our picture looks like. And these types of physical systems that have this picture where one mass is much greater than the other, as it turns out, those types of systems follow this harmonic oscillator model beautifully. And the predictions we can make of these types of molecules is confirmed with spectroscopy with crazy precision and accuracy. It's awesome how well spectroscopy, or really I should say how well quantum mechanics predicts what we observe in spectroscopy. And I'm going to show you some examples of that soon. Okay, so let's talk a little bit about the concepts, and then we'll talk about some cool examples with spectroscopy. Okay, so psi approaches 0 at large displacement. And so what does that mean? Well, if I have a really wide-looking potential energy well, okay, then my psi function is really spread out, right? But if I have a really narrow potential energy well, then my psi function is going to have a much larger amplitude, okay? And the width of this well is given by my displacement scale. In other words, the oscillator frequency and the reduced mass, okay? So psi approaches 0 more rapidly for large masses and large force constants, so stiff springs. And so what that means more rapidly is, as it turns out, this picture that I've drawn right here is a stiffer spring. Okay, so if I go back to this picture where this is oscillating, a stiffer spring would have an oscillation that looks like this, whereas a less stiff spring would have, a slower oscillation. And so what that means, this psi approaches 0 more rapidly. So that means the wave function is falling up and down a lot more chaotically than some smooth, spread out wave function. Okay. So as nu increases, the Hermite polynomials become larger at large displacements. And what that means is psi spreads out over larger areas. So this is, more or less just kind of saying the same thing, but in different ways. And then finally, as nu approaches infinity, psi squared increases at the turning points. And this is another brilliant example of quantum mechanics converging to classical mechanics via the Correspondence Principle. And so the idea of this, here you can see what wave functions look like for 0, 1, 2, 3, 4. Well, what about 20? Okay, so I have to draw my potential energy diagram upside down, right? So my potential energy diagram would look upside down like this, all right? And so what this is showing, as nu approaches infinity, the peak of those wave functions is getting pushed further and further out. And now if we think about just a classical spring, two masses on a spring that can displace a really large distance, if you looked at how much time each of those masses are spending at whatever position they're at, okay, for a large, classical spring, as it expands out, it's decelerating, right? The spring is starting to apply this force constant, so it's slowing down, and for a very, very brief instant in time, it's stationary before it recoils and accelerates back to some compressed position before expanding out and then recoiling. And so what that means classically, a spring is going to look like this, where it's spending most of its time out on the turning points, okay? Quantum, on the other hand, would tell us that the most likely place of finding that oscillator is, in this compressed mode, okay? So again, this is just where the classical mechanics world evolves out of the quantum world as we build up larger quantum numbers, masses, and energies. Okay, so let's look at some cool practical examples. And this is a little outside of what the book goes through, but I wanted to provide you with some actual cool manifestations of this. So here I'm going to have my calculation and then the graph up here side by side. And so what I've done here is I've calculated the wave function for carbon monoxide and HCl using the harmonic oscillator model. Okay, so you can see the force constant for carbon monoxide is quite large, 1860 Newton per meter. And so that would be an example of a very stiff spring because we know carbon monoxide has got that triple bond. Okay, versus HCl, which has a very small force constant of 480 newtons per meter. And that's just because that's a single bond like so, okay? And so what that means, if you were to now use the reduced mass, so again, this m that I used here to calculate alpha, right, was from, mass of hydrogen times mass of chlorine divided by mass of hydrogen plus mass of chlorine, and then same for over here, right, mass of carbon times mass of oxygen over mass of carbon plus mass of oxygen for the mass. And we have to remember when we do reduced mass calculations, we're not doing it for the average periodic table mass. We have to specify which isotope, right? Because a DCl, a deuterium chloride, will have a very different reduced mass than an HCl. And so for those of you in the lab, this is a very cool experiment we can do. We can synthesize HCl or DCl in the Schlenk line and take spectra of it, and we can actually see the difference in the spectra when we replace the hydrogen with the deuterium. Excuse me. Okay, so using the force constant, using the reduced mass, I calculated alpha for carbon monoxide to be 4.8 picometers. And alpha for HCl to be 10.9 picometers. And so as you can see right here, as a result, so HCl is in the orange, its wave function is much more spread out, okay? Because it's not as stiff of a spring. So when it vibrates, it can really elongate. So it physically elongates to a bigger distance, okay? And so you can see that, 10.9 picometer, it's hard to say where is that 10.9 picometer showing up? But again, this alpha, right, because y is x divided by alpha, that really number is just setting the scale for our x-axis. And so here you can see this x-axis now, because I'm using realistic alphas, that's in units of picometers, okay? And conversely, you can see the ground state of carbon monoxide is a much narrower, more compressed spring, which makes sense given that it's got a triple bond. So what's also cool, I calculated the wave functions for carbon monoxide and HCl for nu equals 1. And you can see similarly now, HCl really spreads out as it goes through this transition. Okay? And so now in spectroscopy, what we observe in spectroscopy is the difference between these energy levels, all right? Remember, spectroscopy is the difference between these energy levels, which we know now, if I draw this really quick here, we've got my ground state that looks like this. We've got my second excited state, which looks like this, okay? And we now know the difference between these two energies is given as h bar omega. So obviously each of these molecules will have different h bar omega spacings because they have different oscillator frequencies, they have different reduced masses, okay? And also what we can talk about the intensity of a spectroscopic transition. So for example, if I look at a spectrum here, and let's talk about an infrared spectrum, right? So where I'm going to put wave number with a little tilde, right? versus intensity, I. Okay. So I'll just show you like an example of two different peaks. So let's suppose we saw, a carbon monoxide peak, and then we saw like an HCl peak. Whoa, get out of here. And actually, I should back off. Let's not even call this carbon monoxide or HCl. Let's just call it two different peaks, okay? So the wave number where these peaks appear is given by this equation. Delta E equals H nu, okay? The intensity, so in other words, the height of the peak is proportional to the expectation value of the vibrational dipole moment operator. Okay, so remember, one of the important selection rules of vibrational spectroscopy must contain a dipole moment. Okay? And so I'll talk about this other selection rule, VF equals VI plus minus 1. I'm going to show you that in a moment, okay? So here, so another thing that's important to note with the expectation value of the vibrational dipole moment operator, and so that should be the, I've put too many qualifiers in there, the transition dipole moment operator. So that should read the expectation value of the vibrational transition dipole moment operator. So that dipole moment operator is negative e to the x, where e is the 1.6 times 10 to the minus 19 coulomb. Okay, and so we get a dipole moment when we have a charge acting over a distance, right? So if we think about HCl elongating, all right, and I draw a dipole moment, there is definitely a charge propagating over a distance as given by charge E times displacement x, which is very cool. And the way that this operation works now, take note, okay? Where psi of VF, operator sandwich, psi of VI, where psi of VF does not equal psi of VI. So these are in fact different states, okay? And there's two outcomes of this. When this expectation value is 0, no peak is observed in the spectrum, okay? I'll say no peak. And that's what you learned from OCHEM, right? You learned that from organic chemistry, that a molecule must contain a dipole moment to be infrared active, to have an IR spectrum. And hopefully now you're connecting that this IR spectrum is the vibrational spectrum, okay? So now what if mu, the expectation value, does not equal 0? Well, then we get a peak in the spectrum. And the larger that value is, the more intense our peak is. So these two examples that I'm showing you right here, this peak right here, the taller one, would have a bigger dipole moment operator. Or excuse me, would have a bigger expectation value for the dipole moment operator, okay? So now there's another selection rule that comes out of the woodworks of this. And all of this stuff, this simple harmonic oscillator, is based on the fact that VF has to equal VI plus or minus 1. So in other words, this expectation value only works when you change the quantum number by 1. Okay? And I'm going to demonstrate that for you, not by using math and proofs, but I'm going to demonstrate that for you by actually solving the operator. Okay? So here what I did to make life easier, you can see that I've got a function just defined very easily. So wave function, and then the way my notation works, so xco, so I'm calculating the displacement of co. And so you notice here my dipole moment operator is negative e times x. Well, if I get rid of the e, and then I just have the displacement operator, which is just times x. And because e is a constant, I can multiply it by e after the fact. Okay? So what I've got here now, alpha CO, so that's going to use my alpha carbon monoxide value. I've got my whole wave function defined in terms of x. And then check it out. I've just done this as the operator sandwich, right, to calculate the expectation value. Psi x psi. But now look, I've made, so this term right here, 1 and 0, that's for my quantum number nu. So here I've made nu 1, and here I've made nu 0. Okay, so let's try the 0 and 0 case. And I'm also doing this for the HCl molecule. Let's make that 0 and 0. And then now what this next line does is it converts my units into a debye. So dipole moments are given in units of debye. All right. And 1 debye equals 3.3, I'm copying it off my Mathematica right there, 3.3356 times 10 to the negative 30 Coulomb meters is the unit of a debye, okay? And so what I do now in this operation, so that's that XCO, right? That's going to give me that value. I calculated that value in terms of picometers, but then now my times 10 to the negative 12 converts it into meters. Here's times my E, 1.6 times 10 minus 19, and then now dividing by the 3.33 something something, that's just going to put it in this nice easy unit to use, which is the debye, okay? So now check it out. Let's do it for 0, 0, 0, 0, and shift enter, and what do I get? Look at that. So here's my results, right? The expectation value for carbon monoxide and then for HCl, 0 and 0. Of course, when the quantum number doesn't change, there's no spectroscopic transition. Duh. Okay, so now let's look at the case when it's 1 and 0. So again, follow this notation. The final quantum number is 1. The initial quantum number is 0. We'll do it 1 and 0 for each case, and we'll evaluate. And beautiful, I get values for it. What the actual value is not so important. But what's important is that there is a value. It's a non-zero value. And the fact that it's negative is fine because that dipole moment, we're using the charge of an electron, right? So it's an electron being displaced as it elongates, okay? So really what we've got going on here, if I continue this picture, this is VF, okay? And VI looks something like this, right? A more compressed bond. So this dipole moment operator expectation value is really giving us the difference between those two displacements, okay? Times the charge that's been displaced. And what we could also conclude from this calculation, the HCl will have a more intense spectroscopic transition, so it'll be a larger peak, okay, than the carbon monoxide peak. So now let's play with this. Let's do something cool. What happens now if I make this 2 and this 2 and I still keep these as 0? No spectroscopic transition. Okay, 0, 0. Well, what if I make this 2 and 1 and 2 and 1? Well, that's still giving me that selection rule that nu f, or that nu can change by plus or minus 1. So let's evaluate that. Great, I got values, and I'm still predicting that HCl would be a more intense transition. And so that's in the case of 2 and 1 and 2 and 1, which is a difference of 1. Just to prove to you that I could also do this backwards, let's make this 1 and 2 and 1 and 2, because not only will that describe, when it goes from 1 to 2, it's absorbing light, but when it goes from 2 to 1, it's emitting light. And let's evaluate that. And I get the exact same answer, which is to be expected, okay? But now, what if I go up to, let's say, 3 and 2 and 3 and 2? Yep, I get a value because it's plus minus 1. But what happens if it's 4 and 2 and 4 and 2? Nope, no dice, okay? So this is a really important selection rule in vibrational spectroscopy. You've already learned that a molecule must have a dipole moment to have an IR spectrum. But also, in an infrared spectrum, which is a vibrational spectrum, it can only change by one quantum number at a time. So what that means in IR spectroscopy, in all IR spectroscopy, okay, you're always probing what's called the fundamental transition. And the reason why this is called the fundamental transition is because if we go back to the statistical mechanics, right, we expect 99+% of all molecules to be in their ground vibrational state. And so when you put some molecules into an infrared spectrometer, the only transition it's looking at is the 0 to 1 state. Okay? So now you might imagine when you have a complicated molecule that has a lot of these oscillators, luckily you're only viewing one transition per functional group, right? Because if there was multiple transitions, so if let's say 0 to 2 were possible, or 0 to 3 were possible, your infrared spectrum would be nearly impossible to interpret. Because, for example, your carbon-hydrogen bond would have a 0 to 1 peak, a 0 to 2 peak, a 0 to 3 peak, right? It would be all over the place. So in IR spectroscopy, vibrational spectroscopy, we only probe the fundamental transition from nu equals 0 to nu equals 1. Okay? And so finally, the last thing that I'll show you here, the last calculation that I did, so we noticed that the energy levels are given as h bar times omega. So I calculated that right here. So this is h bar times omega in my Mathematica file. Okay? And I wanted to convert it to wave number to the unit of centimeter, which I did through all of this stuff. And you'll do this in your Mathematica assignment. And so check it out. So just using the simple harmonic oscillator model, not even looking at the spectrum, I get that the frequency of transition for carbon monoxide to be 2145 wave number, and for HCl, 2882 wave number. That is damn close, really, really damn close to the actual wave number transition that's observed in real life. Okay, so think back to your OChem days. See, remember, go back and look at your notes if you have to. You'll see that when you have carbon triple bond, it occurs around 2100 wave number. When you have a hydrogen chlorine bond, it's occurring around 2900 wave number. A hydrogen oxygen bond occurs around 3300 wave number or so. So this is very, very cool. This is amazing to me, the stuff that can be predicted here just with this simple harmonic oscillator model. All right, folks, that's it for vibrations, just 2 lectures. So I know both of these were a little long, about 40-ish minutes each, but that's it. That's all we're gonna do with vibrations. We're gonna come back to this in our spectroscopy section and really get into this in more detail, okay? So, know how to normalize the harmonic motion Schrodinger equation. I did that. Know the wave function profiles, okay? Be familiar with how QM converges to CM for harmonic oscillators at large quantum numbers. And be familiar with realist examples of harmonic oscillators, such as HCl and CO, and be able to calculate their properties, such as vibrational energy levels or transition dipole moment operator expectation values. We're going to get practice with that in the Math 5 assignment. Okay, folks, I will see you later.